When you are reporting a classifier's performance in a paper, or when you are pitching your results to a customer, what information do you present? Some cross-validated metric like accuracy or the F1 score? Such metrics are helpful in IID settings, where your validation data is distributed exactly like the data you will later deploy your model on. But what if validation and deployment data are distributed differently from each other? For example, imagine your validation set represents each class by the same number of samples. And imagine you are reporting accuracy, with 78% of your predictions being correct. If the deployment data has the same class proportions as your validation set, everything's fine. The true accuracy will be close to the value you have computed. But if the class proportions are subject to change, your score will be mistaken. You are falling victim to a phenomenon that's known as label shift or prior probability shift, which can become a trust issue if your audience is already expecting label shift in their use case. The question is, how robust is your classifier against shifting class proportions? To build trust in your classification model, we propose a certificate for model robustness under label shift. Our certificate emerges from learning theory and is backed by PAC bounds. What it declares is the set of class proportions for which your model is probably and approximately correct. In other words, it declares all magnitudes of label shift that do not hurt your model, which is an interpretable notion of label shift robustness. Computing our certificate is straightforward with the code that we have published. Simply feed it with your classifier and with some validation data. And check out the range of class proportions for which your model is safe to use. The larger this range, the more robust is your model. Our experiments show that this certificate does keep its promise. The true loss of a model, which we do not know in practice but which we have simulated here, never exceeds the loss that is predicted by our theory. Your readers and your customers can trust the guarantee that our certificate gives. If you're interested in the theoretical and technical details of our proposal, you can always take a look at our paper. To get you started, we'll now proceed with the course outline of these details. Our original motivation is the learning task of active class selection, where the goal is to optimize the proportions of classes in newly acquired data. The foundation of this task is a class-conditional data generator, like an experiment or a simulation. We repeatedly ask this generator to produce feature vectors for the classes we choose, to continuously improve some classification model. The free choice of class proportions in the training set often introduces label shift. Therefore, we chose this task as our motivation. However, our certificate is also valid in any other setting where label shift occurs. To formally analyze label shift, we consider a target distribution T, where a model is to be deployed and where it's required to be accurate. We further consider a source distribution S, where this model is being trained and where the label shift occurs. From S, the actual training set D is a random draw with a finite number of examples. Looking at the losses, this random draw might not represent the target distribution as well as we would like it to. The total gap between the sample loss and the target loss should be as small as possible. Since the training set is a random draw from the distribution S, we know from standard PAC theory that there is at most some epsilon error between the losses of S and D. As we increase the size of the training set, this epsilon is tending towards 0. For large training sets, all that remains as a total gap is therefore close to something we call the inter-domain gap between the distributions S and T. In active class selection, this transition happens naturally while more and more data is being acquired. In binary classification, specifically, the interdomain gap reduces to a product of two differences. First, of the difference between the class probabilities in both distributions S and T, which we denote as delta P. And second, of the difference between the class-wise losses, delta L. If one of these differences is 0, so is the domain gap. If one of them is non-zero but fixed, the domain gap will grow linearly with the other difference. and so will the total gap, which we observe as an effect of the shifting class proportions. For certification, we are therefore interested in the largest delta p, which still results in a small domain gap with a high probability. This value will characterize the robustness of our model. To find it, we need to estimate the other difference, delta L, from the data we have. More precisely, we need to find, among all upper bounds that exist for delta L, the smallest one that still holds with a desired probability. Once we have such a smallest upper bound, finding the largest delta p is just a matter of rearranging the equations. What we finally get is the range of binary class proportions for which our model is accurate with a high probability, even despite shifting class proportions. In other words, we've just certified our model in terms of the class proportions that it safely handles. Our paper also provides an algorithm to estimate delta L from your validation data. More precisely, a constraint optimization objective to do so. You might also find interesting that our theory even motivates a quite successful strategy for active class selection. If the reviewers are gracious, we will present this strategy at the Interactive Adaptive Learning Workshop here at ECML PKDD. In any way, thanks for watching and stay tuned. Our analysis is currently limited to binary classification into decomposable loss functions. Future work should extend these results to multiclass settings and to non-decomposable losses.